Hi, I'm back. This is Chapter 7, Video number 2. Okay, let's resume where we left off, friends. I was explaining the standard deviation, and this is going to be a way to measure risk because it takes possibilities and looks at how much they tend to deviate from a measure of central tendency. In our case, that's going to be our expected rate of return. I use 10% as an example for two companies. Now, sometimes the deviation will be very wide and short, and other times it's going to be very steep and tight around that 10% line. Okay, but in both cases they are bell-shaped curves. So it stands to reason, now keeping in mind that under that curve in the Galton box, that accounts for 100% of the possibilities. Okay, in a natural process, you won't reach 100% because there are no edges to that Galton box. Your possibilities can go out to infinity on either side. However, the odds of that happening are unbelievably slim, okay? So we're going to take any curve, I don't care if it's the tall skinny one or the long wide one, and split it into 6 different pieces, 6 equal increments, and each one of those is known as a sigma, okay? So I took our 3 possibilities for Jackson, okay, 5%, 10%, and 15%, and gave them a representation of the 3 bars, which represent 25% probability and 50% probability. And you can see that they suggested a smooth bell-shaped curve. Now remember, we're not interested in 3 measurements. Using those 3 measurements, we're going to develop the bell-shaped curve, and that gives us all of our possibilities. Okay, Conway, as you might expect, is shorter, but very, very wide, very widely dispersed. It's still 10% at the center, but you can see that the possibilities of going away from 10% either way are greater. Therefore, intuitively, we know that Conway is going to be the riskier of the 2 companies. Okay, so if we can take either of those curves and split it into 6 equal pieces, each one is called a standard deviation or a sigma. All right, you can see that the number for Conway's sigma is going to be much bigger than 1/6 of the curve for Jackson. Okay, so the smaller the sigma, the less risky the company. That's going to be our general principle. Okay. All right. Once again, remember that we can account for, under 6 sigma studies, we can account for almost 100%, but not quite, of the possibilities. Okay. In a Galton box, all the marbles are there. Without those edges, one marble might have a chance, just a slight chance, of rolling way, way out beyond the edge, okay? Those are infinite numbers. They are asymptotic numbers, okay? Again, this is not a math class. I won't hold you responsible for that term, but I did tell you once before what it meant, okay? So once you mathematically determine the value according to Dr. Poisson or Sir Galton and all of the people who studied their rules later on through history, once you know the size of 1/6 of that curve or a sigma, then you've got a rule that you apply. And this is the general, and I say general rule because nowadays this is a bit old-fashioned. Now we carry it out to 99.9997% of all possibilities being 3 standard deviations from the mean. Okay, we've gotten much tighter. For this class, we'll call it 68.3%. That will be all possible outcomes. This is general rule. It's always going to be 68, 95, 99, okay? If you take your center point, 10% in this case, minus 1 sigma, which we'll calculate, plus 1 sigma, that space above and below the 10% mean is going to account for 68.3% of all possible outcomes. That's a natural rule that Poisson determined. All right, now take that same number, the central tendency, 10%, and subtract 2 sigmas and add 2 sigmas. That range will account for 95.5% of all possibilities. And finally, 99.7% of all possible outcomes will be plus or minus 3 sigmas from the mean, okay? And we will do the calculations, okay? And I've actually sketched that out for you in the book. That, by the way, is the formula for standard deviation. Back to that in a moment. Let's scroll down, there it is. Standard deviation is within a normal distribution. I don't care whether that curve is tall and narrow, or whether it's short and fat, okay? Plus or minus 1 sigma around the expected rate of return. Chances are 68. That's a typo. That should be 68.3. I apologize. Of all possibilities will happen within that range, okay? And you can see that we account for more and more of that curve the farther out we go. I'm just making a note to correct that, okay? All right, very good. So that's the master mathematical rule. 68, 95, and 99, okay? So that's what we will be using in the problem I asked you all to try for me, problem number 4 at the end of the chapter. Okay, now let's move backwards a little bit. Okay, bear with me. There it is. That's the button I'm looking for. So, know those 3 numbers, please. Don't memorize them, just know where to find them and how to apply them. Now we'll actually calculate the standard deviations, okay? The mean, the center point of our bell-shaped curve, no matter what its height or width will be, is going to be the expected rate of return. In this example, it's 10% for both companies. That standard deviation, therefore, measures risk. Okay? All right. And this is what I just said. Conway, with its greatest sigma, is the riskier of the 2 companies. The master rule, the greater the sigma, for now, the greater the risk. Okay? Calculate sigma, and now you'll know which of the companies has the most risk. We're going to change that rule in special cases later on. Okay? So what I'm going to do is I'm going to skip back to the book here for a minute. Okay? Now let's go back to this formula. That formula, and I don't expect you to memorize this, but if you're into stat or into formulas, that is how we calculate the standard deviation that we're about to do. We're going to do it on a matrix. We're going to do it in Excel, okay? Now, if you're really, really a heavyweight, a gunslinger when it comes to math and statistics, you might look at that and say, wow, wait a minute. That's not the exact same formula that we used when we studied standard deviation. Well, there's a reason for that. Go check out the, at the end of the book where all my chapter notes are, okay? It looks like it's footnote number 7 to chapter 7. And yes, the formula is different if you are looking back at actual results. We have to tweak the standard deviation formula a little bit. I give you that at the end of the book in case you're curious. Here we're not dealing with actuals, we are dealing with expected possible future outcomes and their probabilities, and therefore the standard deviation calculation has to be a little bit different. Okay? So if you had any curiosity about that, that's the answer. All right, now here's how it works. And again, use Excel for this, okay? First, I list in column 1 the returns. For Jackson, they were 5%, 10%, and 15%, respectively, in a weak, a normal, or a strong economy. We write down in column 2 the expected rate of return, 10% in all cases. In column 3, I deduct the ERR in column 2 from the return in column 1. Okay? In column 4, I take the number in column 3 and multiply it by itself. I square it. Okay? That gets rid of negatives. When we're calculating sigma, we don't care whether something is good or bad. We care about how far it deviates from the central tendency. So squaring something and then later on undoing that square gets rid of negative numbers because, as you know, when you multiply a negative by a negative, you get a positive. Okay, so then, now here's where the standard deviation calc is different than an actual. Now what we have to do is reassign the probabilities that our economist gave us, 25% odds, 50%, and 25%. Multiply column 4 by column 5 and put that product in column 6. Add the values in column 6 up. I've got 3 of them. You might have 5, you might have 7, you might have 8, okay? Depending on how richly, how deeply the economist drills down into her data. Okay, that number is what statisticians call a variance. I have no idea what the variance is or does, But I know one thing. If I take that number and take the square root of it, all right, the square root of the variance is sigma. That is your standard deviation. Follow this exact procedure and you can't go wrong, friends. Okay? All right. 3.54 times itself would give you 12.5. So do the opposite. In column 4, we squared something. Over here, we take the square root. All right. 3.54 is the sigma for Jackson. I do exactly the same thing for Conway. Okay? There are Conway's possible returns. Okay? And I follow all the same procedures. I add up all my products and I get the variance. And my sigma, once I take the square root of 312.50, is 17.68. Okay, depending on what you're applying it to, that number can mean anything, but in this case, it represents a percentage, okay? So, that is 3.54% for Jackson, 17.68 for Conway. We immediately conclude, as we already intuitively knew, that Conway is the riskier of the two companies. Okay? All right, very good. That means, just take Jackson. Using the mathematical rule, okay, let's pull this thing to a conclusion. We conclude that if the sigma is 3.54 and the ERR of Jackson is 10%, then 10% minus 3.54, that's one standard deviation below the ERR, and then take the same 10% and add 3.54, okay? That gives you a 1 sigma range around 10%. That means that there's a 68.3% chance on master rule that even though you expect to make 10%, your return for Jackson could go as low as 6.46% or as high as 13.54%. That's your risk. Plus or minus 2 sigmas means there's a 95.5% chance your return could be as low as 2.92% or as high as 17.08%. Okay? So once again, instead of 3 bars, like we saw when we started, those 3 bars were turned into a bell-shaped curve under which all of these possibilities could fall. Okay? Study this carefully for me, friends. Now, one final thing I did is I plotted those 2 curves together. And in order to make it valid, I changed the name of that y-axis to probability density. Don't worry about that. You're not responsible for that. I did so only because I wanted to put both bell curves on the same graph. You'll notice that the shape is pretty much as we expected. Okay? And even though I drew these by hand using software, I tried to make them as accurate as possible based on the numbers that we just derived in our 2 matrices, the 3.54% and the 17.68%, respectively for Jackson and Conway. Okay? And again, we see that Conway is the riskier of the 2. Okay, now, what happens if the 2 rates of return are different? I forced them both to be 10%. But now I want to put those 2 curves in different places on my y-axis. Okay? So let's get back to our slides here. Any other conclusions? All right, Jackson's worst expected news is 5% return only, and they are limited to 15 on the high side. Conway, you may get a loss, but on the upside, you could get a much greater reward, 35% instead of 15. So if you are risk averse, you will accept those constraints for Jackson. And if you are a little more risk tolerant than I am, then you might say, yeah, but I want that chance to make 35%, and I'm willing to risk a loss in order to get it. So if you're more risk tolerant, you might choose Conway. There's more upside potential. Now, please remember, circumstances are researched and assumed. We have no idea if our economist is right. You line up 3 economists or 3 dozen economists in a room, and they may come up with all different opinions. And secondly, to make matters worse, what happened in the past does not always indicate or guarantee that the same things will happen in the future. So you've got at least 2 variables here that could end up being all over the map. Please be aware of that danger. Our goal is to tip the odds in our favor to become richer by understanding the technique. All right? Now remember, the bars are misleading. I put them there only to show how numbers can be turned into a bell-shaped curve. All right, don't worry about probability density. Okay, so for now our rule is the greater the sigma, the greater the risk. Here's the condition, ladies and gentlemen. If the ERR is the same for both companies, I forced it to be. However, if the ERR for each company is different, that could change your conclusion. So we're going to change up Conway, and I'll refer to the text. If I can find it. Ah, there it is. All right, I'm going to leave Jackson right where they were, but I'm going to change Conway. So I'm going to redo their returns. I'm going to keep the economic conditions the same, but when I look back on their past, let's assume instead, like it was a loss of 15, 10% normal, all the way up to a high of 35%. This time I'm going to change it up. If there's a weak economy, Conway makes 32%. In a normal economy, they make 40, and in a strong economy, they make 48. Do the math the same way, and my expected rate of return for Conway is no longer 10%, it is 40%. I then use that data to come up with a new standard deviation. Instead of 17.68, I'm going to keep 3.54 for Jackson, but Conway will change up. There are the new returns, there are the new calculations, and there is my new standard deviation. Okay, so Conway has been revised to 5.66. They are not as risky as they were before. The spread between these numbers is a little tighter. It's still not as good as Jackson. So if we were working only looking at standard deviations, we'd come up with the same conclusion. 5.66 sigma is a little bigger than 3.54 for Jackson, so Conway would still be riskier. However, okay, because the two ERRs are not the same, we're going to give it a second test called the coefficient of variation. It sounds fancier than it is. It's simply a matter of taking the sigma divided by the ERR. It's very, very easy, in spite of its formidable sounding name. Okay? So if you stick just with standard deviation, it does look like Conway is still riskier, but now we've got to apply a second test to it. We can't just stop at the standard deviation. You can only do that if the ERRs of the two companies you're comparing are the same. Is Jackson still the safer choice? Okay, now Conway's return could be as low as 23% or as high as 56.98%. With what kind of certainty? 99.7% certainty, plus or minus 3 standard deviations. But the curves are separated. The standard deviation is not good enough. That means that on Jackson's very best day, they could make plus 3.54 standard deviations, they could make 21%. They might. But on their worst day, Conway, the new and improved Conway, their worst day, minus 3 standard deviations would make more than that, 23.02, because they have different ERRs now. The curves are separated on the x-axis. So even though Conway has a higher standard deviation still, we need to throw the rule of standard deviations out and apply a second test. Common sense says Conway's worth the risk. Its higher ERR makes the difference. On Conway's worst day, it'll make more than Jackson on their best day. The coefficient of variation means the amount of risk per unit of return. All right? The CV, as we call it, you're going to take the sigma and divide by the ERR. In the case of Jackson, that's 3.54, their sigma, divided by 10%. Okay? All right, now the rule is this. The higher the CV, the riskier the stock. Okay? The lower the CV, the safer the stock. Smaller is safer, both with the standard deviation and the coefficient of variation. All right. Now, if the ERRs are the same, here's our rule. The standard deviation governs. Stop. Elvis has left the building. You use it. But if the ERR is different, you have to give it a second test, and the CV may come up with the same conclusion. Great. But sometimes, like in this case with Jackson and Conway, the CV and the standard deviation might contradict each other. What do? The CV trumps the signal. So if they give you different conclusions, you throw out the standard deviation and always use the CV. Here are the numbers. The sigmas that we calculated for Jackson and the new Conway were 3.54 and 5.66 respectively. The ERR was 10% for Jackson, we left that one the same, and 40% for Conway. The CV maths out to 0.35 for Jackson, 0.14 for Conway. Conway has less risk per unit of return, smaller is safer, so now a risk-averse investor would still end up going with the more favorable company, which in this case is Conway. Okay, so I placed those two curves in their new places on the x-axis, and that illustrates that Conway does have a wider bell curve. Your instinct tells you it's riskier, but it really is not, because the tail end of Conway's red curve is, or pinkish, whatever color you want to call that, is still higher on the return line than the high side, the green line, of Jackson's good news. Okay, so that's why the CV is so important to us. Okay, my time is up. I'm going to have to land the plane right here, ladies and gentlemen. More will come. You have enough information now to do all of problem number 4 at the end of the chapter. Please do so. As I made a posting a while ago, and I will come up, depending on how far we get in this chapter and anything I choose to omit, I will come up with more assignments for you. Happy viewing and have yourself a nice evening. Bye-bye.